Hey everybody, this is Larry. Hit the like button, hit the subscribe button. Let me know how you did on this problem. I'm going to solve it live right about now. 1140, Stone Game 2. Alex and Lee continue their games with powers of stone. There are a number of powers arranged in a row, and each power has a positive integer number of stones, powers of I. The objective of the game is to end with the most stones. Alex and Lee takes turn, with Alex starting first. Initially, M is equal to 1. On each player's turn, that player can take all the stones in the first x remaining power, where 1 is less than or equal to x, less than or equal to 2m. Then we can set m is equal to max of mx. The game continues until all the stones have been taken. Assuming that Alex and Lee play optimally, return the maximum number of stones Alex can get. So I think I solved this problem a long time ago. So I'm going to, but it's dynamic programming, so I'm going to try to do it again because it's always good to get practice on dynamic programming. I think the thing that I got stuck on last time was that I got confused with the X and the M, but I'm going to go over how I would solve this from beginning to end in the first place. But yeah, so the thing that I would think about is what is N, right? N is 100, so that's, well, let's set this up in code first maybe, doesn't really matter. So there are a couple of components that I always think about when I think about dynamic programming, and I think about, is it a prefix / suffix dynamic programming? And what I mean by that is that if you go from left to right or right to left, is there some kind of thing that you can hold as an invariant or hold as a true subproblem, right? Meaning there's some problems where you go from left to right. Well, you can because the ordering either doesn't matter or matters in a way that you can't just take the first element and see what you can do with it. But in this case, you literally are told that you only given stones in the first X pile or something like that. And when I see something like that, I immediately jump to something like, okay, it means that when let's say you take the first two elements, right? So you go from here, this array to this array, right? By taking the first two elements, and here, when you're here, let's say the question is, or the problem or subproblem might be that, let's say we're giving this array, will the best answer given this array lead to the best answer given that array? In some way. It doesn't have to be a one-to-one. That's where we sometimes have for loops in the transitional states and stuff like that, right? And in this case, it feels like it makes sense that this is the ideal state because you could consider them as sub games and stuff like this, and that if I take these two, then my score is just 9 minus the opponent's turn to take this score, right? Well, maximum number of stones. So yeah, okay. So this requires a bit of game theory, something called Minimax, which is a little bit tough to explain in a short stream. But the general idea is that, let's say I'm Larry and I'm playing Alex or Lee in this game, and the best thing for me to do, because the scoring is linear, and what I mean by linear is that there's just addition and stuff like this, that the best thing I can do is get the best score such that I take the highest score and also minimize my opponent's opportunity for the max score. So the minimum score for them and the max score for us. And in that case, this actually is a lot of the complexity, right? Is that, okay, so you can iterate through the loop this way in that, let's say we take 2 and then, this is the subproblem, and then this is actually a subtract, right? Because we want to subtract it from what our opponent might get as a score. And then now it's 18 and then 4, 4 and so forth, right? So these are the things that I would think about. This is game theory-ish, game theory, dynamic programming, and this is Minimax. So those are the things that I would Google on a little bit, because maybe it's a little bit out of the scope of how, we could do a whole chat about this, whole video about this. So yeah, so that's one of the possibilities. But now the constraints, right? So now let's, in theory, I would set up my thing like, okay, let's just say get max. And then, I usually name these index. You could use your whatever, but index would refer to the number of things that we processed from left to right in this case. And then now, our additional thing is that we can only choose x to be between x 1 and 2m, right? So that means that we probably need this m somewhere. And that's fine, because what can m at most be? Well, m can at most be n, right? Because, I guess in theory it could be bigger than m, and m can be bigger than n. But if m is bigger than n, you just take the entire thing anyway, right? So in that case, in terms of analysis, well, how many possibilities are there for index? Well, index can be from 0 to n, give or take -1, and m can be from 0 to m, or maybe 1 to m, but give or take, right? And what I'm saying here is that now the number of possible inputs is O of n squared, because it's n here, n squared, right? Okay, and that is good enough for us to start. The thing is that I would also think about, as we kind of saw here, we would iterate through the m. So the number of when I first think about states, there's O of n states, O of n squared states, and each of them would take O of n time. So roughly speaking, and this is back of the envelope, it just kind of gives me a number to think, okay, do I have enough to start working on this problem, to start programming, right? And here I have a roughly n cube algorithm, and we could prove, and we will prove this later. But I just want to give the back of the envelope to, like, is it worth programming? Because, for example, if we do the math and we're like, oh, this is n to the 5th, and n is 100, well, that's going to be way too slow. So there's no point of programming it out, because that's going to get time limit exceeded. But here it's 100 to the 3rd, which is fast enough. So then we're like, okay, this should be good. So let's get started on that. Yeah, what is the initial? Oh, initially m is equal to 1, so that just sets our initial states. So we, okay. So now, if index is equal to n, we're done. So then we could just return 0, because there's no more stones to get from either side, right? And then otherwise, we want to iterate we have to take at least one stone, and then we have to take it all the way to possibly 2 times m, right? So now we can even use their notation, which is for x is in range from 1 to 2 times m plus 1, because it's exclusive in Python. But basically, this is just going from x to literally 1 to 2 times m. And then now, let's just keep track of the best or max score is equal to, actually, so you can actually have negative score, because that means that your opponent has a higher score than you do, right? So this actually has to be negative infinity. Yeah. And you can prove that this will always terminate, because this always gets to 0 at some point. So you always get, at worst, a lot of negative scores. But now, what is the score here, right? Well, the score is, let's say we take the first x from index. So, and there are a couple ways to do this, and we'll kind of go through it step by step. And there's an optimization here that I forgot about, but that's okay. We'll figure it out. But basically, you want something like sum of the first x element, right, from index to index plus x. So that's what we're going to do. Powers of index to index plus x. So that allows us to get all those elements. Maybe it's off by 1. Always curious about that, but let's say that's the case, right? So that is the score we get from collecting the first item, and then the first 2 items, and then the first 3 items. So that's the sum of these things. And then, so that's our score. That's how much thing we got. So stones is equal to this. And then now our recursion is that, okay, best is equal to, well, let's skip that for a second. So the actual score here, that's the number of stones you picked up. The score that you get is equal to the number of stones that you picked up minus the max that your opponent could get, right? So it's index plus x. X being that, we chop off, like if we took off the 2, then we can't use it anymore. So that's where we're starting from. And then what is the new m? Well, m we set to the max of m or x. So we just literally just do that, max of m and x. And then that's pretty much it. And then now we can do best is, now that we get a score for this, for taking X amount of stones, now we can just get the best high score of doing this and score. And then at the very end, get best, or return best. And yeah, that's the way I would think about it. This will time out, so give me a second. We said that this is dynamic programming, and here, this is for each state, O of m work, right, for this for loop. And then now we just have to do, we have to call it, get max of, what do we start? Well, we start with index is equal to 0, and then initially m is 1, so we could just do this. And that's pretty much how I would think about this problem. There are a couple of things we still have to do, obviously, but I might have an off by 1 somewhere, because that should not happen. Yeah, okay. This makes sense because it's very natural to write this as index is equal to n, but which is very natural from left to right. But index plus x can go past n, right? So let's just make bound this by n, so that it cannot be bigger than n. It just takes the rest of the element. Wrong answer, huh? Oh yeah, that's right. So this gets you the max score. This gives you the score of the delta of the scores. And what I mean by that is -6 is the score of your score minus your opponent's score. And apparently the best you can do is just -6. That means you lose by 6. So how do we back that out to get 10, which is the number of stones that you have? Well, in this case, you have to solve another one, which is kind of messy. But this is just the sum of, we sum up all the piles. You could do the math that way, right? So basically, total is equal to my score plus your score or someone else's score, opponent's score, opponent's score. So yeah, my score is equal to up score minus total, right? Wait, is that right? Nope, the other way. So total minus op score, right? So that makes sense, but then we have delta. So delta, we have the other formula. Actually, I've done it the other way. So delta, because that's what this returns. Delta is equal to my score minus opponent's score. So then now you can subtract these two formulas directly. So you get total minus delta is equal to, actually plus. Math is terrible. Algebra is hard. But yeah, you add total plus delta on the left side, and then on the right side, the opponent's score cancels out. So now you have my score times 2. So that's the formula we need. So now total is equal to this, and delta is equal to this. So then now we just have to return total plus delta divided by 2. Cool. Yeah, so again, this will time out, and you could practice this real quick because we said it's memorization, but we didn't do the actual memorization part. Though we did analyzing a little bit, but I think even this will be good enough for it to time out, just to kind of illustrate a little bit. Banana. Yeah. So now that we have this function and we did the analysis already that the number of possible inputs is n squared, so that's great. Let's cache this. And again, I know that a lot of people would in Python now do LRU cache because it's cool, but I always advocate doing it manually and code this out so that you have an idea of what's going on, especially over arrays. But yeah, let's just do cache. I call it cache because I consider it kind of like caching. Let's do 0 for this times n for in. So what this does is it. I think I have to do +1. Maybe not, but just in case. And also, we have to let's convert this to be less than n, because if it's more than n, you just take everything anyway. So then here we can bound everything by yeah. So this is our cache. This just creates an n by n matrix of the caching value. And then now I have has cache, where it just lets me know if there's a cache at that position. There are also different ways to write this. Play around with it, experiment with it, and then let me know. And then here, that's just, yeah. Now we can do if cache, if there's a cache for this index, we just return the cache. And then if at the very end, let's just set, like, okay, now we're good. So let's set the cache as equal to true. And cache of index is equal to best. And then now we should get rid of the timeout or time limited exceeded. Yeah, and brazenly fast, roughly speaking. And yeah, am I good? Yeah, let's submit it. Maybe I should have tested some empty cases actually. Okay, cool. I did it much faster in C, apparently about a year ago. Whoops. But yeah, so that's how I would solve this problem, dynamic programming. And yeah, the complexity, the space complexity hopefully is obvious, because we literally create a space for this, so it's n squared. For time complexity, the way that I break it down is always time complexity is equal to the number of states times the work per state, right? And in this case, this is equal to the number of states is n squared, and for each of those states, we do O of m work where m is less than n. So we can say this, which is equal to L of n cubed, and that's how we come up with the n cube algorithm. The one thing you might wonder is, why is it so slow? The reason is because we do this sum a few times, and actually I forgot about it. I talked about doing this optimization. But the thing to notice is that because for this, let's say we're giving a big array, this actually creates another for loop. So I lied a little bit in that we assume that this is O of 1, but this actually creates like a double for loop statement. So now each state is equal to O of m times m, roughly. I mean, which makes this O of n to the fourth, right? So now you're like, well, I mean, we submitted it's fast enough, but it's still really icky, right? And it's not strictly n to the fourth in the sense that it's 100 to the fourth power. There are restrictions that are created because x has to be less than m, and m is smaller than n or something like that. So it's not strictly that, but it's still not great. So what we now want to do is another optimization is like, well, can we solve this part? Because we look at the code and we're like, okay, this hides a for loop in a statement. But what we notice is also kind of like a prefix sum, where, okay, what is the sum? What is the sum of index plus x, right? Well, this is breaking down. This is just equal to, this is powers of index plus 1 plus, which is S1 plus powers index plus 2 and so forth, right? And then now the thing is should be maybe a little bit come here is that okay, let's just do a prefix sum. Let's do winning sum is equals 0. Winning sum is added by powers of index plus x minus 1, and then this is just the stones. So basically what happens is that instead of doing the sum every time, whoops, oh yeah, that is just, what am I doing? Instead of doing the sum every time, we just add one element every time, right? Maybe I have an off by 1, but that, oh yeah, because this can go over this can go over n, so but yeah, but this is also wrong for that reason. What we actually want to do is if I just wanted to run it to see if it works, but index plus x minus 1 is an n, or less than n, then we do this. Otherwise, it just keeps on adding the last one. That's why I was giving the wrong number. But yeah, cool. And then now, let's run it again. Still looks good, so let's submit it to see if we improve that much on time. Hopefully we do, otherwise, well, okay, we do save a lot more time, right? Though still way slower than the C version. I have to take a look at that. Maybe it's just because it's in C, because I don't think I did it any differently. But yeah, but now this is now for sure O of M, and now we get it down to O of cube. So that's how I solve this dynamic program problem. It's a pretty hard, that's a tricky one to be on a medium about. It's probably a hard medium. I would even say it's a hard problem for the most part. I mean, maybe it's a little bit easier for a hard one, but still, for interviews, this is, I would consider a little bit too hard. But because dynamic programming maybe it's okay, it's fair game, but dynamic programming with all this game theory, I feel like it's a little bit too hard for an interview because a lot of people don't have the game theory background, and I don't know if it's fair to ask people to have a game theory background. I mean, it's Minimax, which is not too difficult to understand, but it's still like a little bit weird. In terms of compared programming, this is pretty straightforward in terms of understanding. It's not an easy problem, but there are a couple of components, couple of things that would get you on. But yeah, I enjoyed this problem, and I think the other thing that I should have done actually is just putting all this here so that it doesn't do the recursive step unless it's bigger than n. But that's probably fine. It probably won't speed up that much. But in any case, that's all I have for this problem. Hope that is great. Let me know what you think. Let me know. Let me know if we have any questions, because this is not an easy problem. And for upsolving, if you want to practice, try converting this into a bottom-up dynamic programming. Let me know what you think. Let me know how you did. Hit the like button, hit the subscribe button, and I will see y'all later.